Just a little subtle.
Yes. Good morning. This is Tcpm, so if you're not interested in Tcpm, you might not be in the right room. Okay, so my name is Michael Turkson.
I'm the other Michael.
I'm Yossi.
Co-chairing all this meeting. This is the note you all read when you registered for this meeting and applies for the IETF and applies to this meeting in particular. So we do have a note taker. Thanks, Gori. If you go to the mic, send your name, say it slowly, say your name, say it slowly so it can be taken down in the notes. And if you are in the future submitting a draft which you think this working group is interested in, put Tcpm in the name so we can see it. I'm going to the agenda. So I will present the working group status at the beginning. Then we will have some presentations regarding working group documents. The first one is the APE document. Then we have accurate ECN, TCP rack, then some about the TCPM converters, the TCP converters. And then we have a presentation by Fernando. Are you here yet? So if he makes it in time, we will see a presentation about the bug in the TCP spec. We will have an update on TCP fast open deployment. And if time permits, we will look at the last draft on this list, which already had some discussion on the mailing list. So working group documents finished between the last IETF and this one is the RFC describing Cubic. And these are the working group documents which are active. The first one, alternate backoff, is actually in working group last call still. We just figured out that we don't have a milestone for it, so we have to restart everything. No, that's a joke, but we really don't have a milestone for it. We are trying to fix this. Then we have TCP EDO. There was an editorial update, but it's just updating typos, fixing typos and that stuff. Joe said they are trying to get implementation experience. RTO consider is a draft which expired, so we haven't seen an update, and it's actually, the document is actually expired. Accurate ECN is a document. We have seen an update, and we will see a presentation on it. The same applies to TCP rack. No updates is on the RFC 793 BIS document. TCPM generalized ECN also hasn't seen an update, but it's still both are still alive. And the TCP converters document, we will have a presentation today. So most of the documents are active. Okay, so these are the chair slides. So Michael, can you come up and tell us about the current situation? It is this one.
Okay, good morning. Next, please. That's Abe, all right. We had a review from Microsoft before the working group last call. I'm just mentioning it because that was just before it. Then we updated the draft. In working group last call, first Richard gave a few comments. Also, Michael Tuxen's essentially saying the same thing about some of the ID references being RFCs already, so that's an easy fix. We'll fix that. And he asked if some generic rules of thumb about the beta loss versus ECN adjustment would be in order. Our answer to that was that this really depends on the congestion control. Our draft does recommend 0.8 for Reno type congestion control, and for cubic there is a bit of text somewhere already that says that the results of our tests indicate that cubic benefits from 0.85, but there's no actual specification in our document about this number. Next. Then we got a pretty long list of comments from Marco. Some of them are pretty easy to deal with. First of all, there was a wrong statement in section 4.1 related to the timeout. That isn't really about our RFC. It's just, some argumentation on why use ECN to vary the degree of backoff, and we decided that this paragraph can really just be removed. So this isn't really specifying anything. Then secondly, he wanted us to specify what happens when cwind is as a thresh, because our document now says this is only for congestion avoidance, but according to RFC 5681, it's not clear whether you're in congestion avoidance or in slow start when cwind is at the thresh. So our suggestion is to be conservative and confirm with the previous versions of this document, which say that you only apply this when in congestion avoidance. Now, this is only definitely the case when cwind is bigger than as a thresh. And in line with what Marco also suggested, we could explain that there is a gray area. There is a sentence in RFC 5681 talking about something being in a gray area, which says that this may benefit from additional attention, experimentation, and specification. So we'd like to say that about the case of cwind being as a thresh, as well as cwind being smaller than as a thresh, because that is also something that is worth looking at. We looked at it, but we don't spec it. Next. And then there was a concern about the lower bound of 2 SMSS being introduced in this RFC. Now, that comes from, it's an editorial thing, really. It comes from having to be explicit about what we do with SS thresh, whereas the original text just says reduce it, in line with being the same as loss. At this point, I just want to say that we never intended to change anything about the ECN behavior except for this calculation factor. So we'll just fix the text to make it very clear that we're not changing anything except for this calculation factor. If cwind can be reduced below SS thresh, then so be it. We're not trying to change anything about the RFC 3168 rules except for this factor. And that's it.
Any comments in the room? So I left the working group last call open for this meeting so that if you have a comment, you can bring it up now.
Praveen Balasubramanian, Microsoft. In terms of testing, I saw that there is a research paper and a bunch of measurements on test setups. Has there been any measurement on the internet or any kind of deployment of this yet? And has the source code been absorbed into any OS yet?
For the first question, not that I know of. For the second question, I think we're in the very last stages before that is shipped in FreeBSD.
By default, changing the behavior of ECN?
I beg your pardon?
By default, changing the behavior of how it responds to ECN marks?
I think it's off by default.
Okay, thank you.
Any other comments? So if that's not the case, then I'll send out a note today that I'm closing the working group last call and ask the authors to submit a new document, and then we will progress it. And these are editorial changes, so we don't need another working group last call. But we wait until we have a milestone. We requested. Okay, thank you.
Thanks.
Miriam? It's this.
Yeah, so accurate ECN, we have this draft already for a while, and we're trying to close it up. So in the next slide, there is a quick recap of the problem statement. The problem was that the classic ECN doesn't provide you enough information if you have high levels of congestion. Basically, if you see more than one marking in a round trip time, you wouldn't know at the sender side. So accurate ECN is just changing the feedback from the receiver to the sender and providing you accurate information about how much markings you have seen in the last round trip time. Next slide. Accurate ECN provides capability negotiation and is backward compatible with classic ECN, and it has two ways to send feedback. One is using 3 bits in the TCP header, so basically reusing the ECN bits that are already there from the classic ECN, and also the previously the bit that was previously known as the ECN nonce bit that is now deprecated or not in use anymore. And then it has a second way to provide you even more feedback with the TCP option, but as we know, TCP option might not always go through the path, so you have like this part in the header that you receive for sure, and then the option is kind of optional. Next slide. That's how the header looks like. So you have, and you will still have with accurate ECN, you have the two ECN flags called ECE and CWR. And then the flag that was currently known as NS, the nonce flag, will in future probably be the AE flag, the accurate ECN flag. And that's like what you use during the handshake. And then later on, if accurate ECN was negotiated, this field is used, or these 3 bits are used as a field to provide you a counter. Next slide. This is how the option looks like. Also very straightforward. You have like 3 fields for 3 different counters. The big difference is that the counter provided in the TCP header is a packet counter, and the counters provided in the option field are byte counters. So basically what this also means is that the packet counter does include control packets which don't have any payload, and the byte counters don't include control packets because they don't have any payload. This is all actually pretty simple. The only complexity is actually when to send the TCP option, because you don't have to send it with every packet. That would be a little bit of too much overload. So basically what the draft says is that you have to send a TCP option if the information that you receive basically changes, or if the code point changes. Then if you see a row of congestion experience markings, the draft say you should send the option more often, because that's the part of information that you really want quickly. And then it says you must at least send 3 options per round trip time, where a little bit of the implementation complexity comes from, because you never really know how much more packets you will send in the round trip time and how to distribute them nicely over the round trip time. Next slide. So there is an implementation. This implementation provides the basic functionality, but it doesn't cover all the fallback and special cases. So it's kind of a proof of concept implementation. It's not a full implementation, but it works. It's also a little bit an outdated kernel version, I believe. What the implementation does, it uses the ECN sysctl that's already there and just sets it to a different value to enable accurate ECN. So the internet interface also stays the same. And what we've done so far is that we have, this is implemented with an experimentation option. So we have the value for the experimentation option reserved in the respective registry. Next slide. So just to recap from the discussion we had last time. Last time we had a discussion about what to do with the TCP flag, because the problem here is that the registry actually says the policy is standards action, and this is an experimental document. And we had a hum in the room with the conclusion that we want to assign the NS flag in the TCP header, sorry, the AE flag in the TCP header right away with this publication of this document, to be clear what this flag is used for. And then the process would be with ISG approval. And that's what the document currently says. So basically the status is we got 2 more reviews since the last meeting from Gori and Michael. Thank you very much. I tried to address most of their comments, put some little changes in there. There are a few more things that need more clarification, and I think then the document is ready.
Thank you. Questions?
So this is Michael speaking from the floor. So most of my comments are purely editorial about the wording, but there's one comment that I'd like to raise again, and this is about how to end this experiment if there's partial deployment. Because I wonder about, because we are experimentally assigning the flag, if we do a PS spec that follows, so how do we do that if the PS spec is different from the experiment? And this comes down to the negotiation. And as far as I can see, there's no way to do that. So the negotiation mechanism is not future-proof in that sense. Maybe that's a downside, or any solution that I could think of would burn a TCP option or whatever. So maybe it is the right thing to do it that way. But I'm concerned that this mechanism is not future-proof. And I think this at minimum must be documented and reasoned. Why, due to the scarcity of the header, it's not possible to design a proper negotiation mechanism. And I think this must be documented because it's a downside of the mechanism. And as I said, I see a risk, as I wrote in my review, I see a risk that we have to burn another header bit later. And we don't have many of them. So that's different to the options. We don't have many header bits. And I think at least this must be documented. And this is not only an editorial change of some words. It's something inherently about the mechanism and its downsides.
Yeah, so my take is that the things that we flag as questions we have for the experiment are not things that change the mechanism basically in itself. It's things that if you change them in a standard track spec, you can just implement them differently and it's no problem, no compatibility problem. For example, the question about how often to send the TCP option, there's the receiving endpoint doesn't have to rely on a specific rate it gets or whatever. It's really just the one who sends the option has to decide on it. So I don't see, for those questions we have in the experiment, that we have flagged out that there's a compatibility problem.
But
so my hope is really that if we see deployment with this negotiation, that means we're on the right track, this is used, and the changes we can do, we can just do. The other case is that we don't see any deployment, and then the end of the experiment would be like we don't use it, right?
I fully agree. But as I said, I mean, we don't know what will happen as part of the experiment. We don't know the future. I have no specific concern right now. It's just my point is, if we run into an issue that requires a change, we have burned a bit.
Yes.
And there's no way to undo that if there's partial deployment. And I think at least that must be well documented, that is that's in property of the design, and it must be documented.
Yep, we can document it.
Michael, can I just ask a question of you before you go away, in case? I'm just trying to understand what you mean by burning a bit, and this is Bob Briscoe for the Scribe, because we're using a bit that's already been used, so in a sense we're not burning a bit, and we're also reusing, we're using it for negotiation, and we're repurposing it during data transfer.
To be honest, it was not used in the SYN.
Yeah.
There are two different aspects. First, this bit was probably never used. It was there was a documentation for a proposal how to use it, probably was never used. But okay, we can decide in this group we will use it in future. That's not my problem. My problem is if we do a PS spec of this and we have to change the protocol as outcome of the experiment, we have to burn another bit. And I'm concerned about the second bit, not about this one here. This is the second one that I'm concerned about.
But I think you will have, no matter what you use all these bits, all the few remaining bits for, you will have always the same problem. Like as soon as you assign a bit and you start deployment, it's really hard to take it back.
There would be a way for, I mean, I've not done the design, but there would be a way, for example, to use the bit now together with an option, and in the PS spec you remove the option. And then you would be able to distinguish whether you run the PS spec of the protocol or the experimental one. So that there would be ways to solve it, but it burns bits elsewhere in the header. So that's the downside.
I understand.
Praveen, Microsoft. I had a question. So the draft says that some of the usages of the option are a must still. So it doesn't leave room for an implementation to not implement the option if it chooses to.
So I did a minor change there actually, because like we had in mind that it's a receiver side decision to use the option, because if you know you're in an environment where options don't use, then don't use it, right? So we flagged this out a little more explicitly. That was like a hidden assumption we had in mind. And I added a sentence somewhere that hopefully clarifies that part.
It still says that, you still must parse the option if you receive it, right?
You must parse the option if you receive it. Does it? No. You must pass the option if you receive it? Like you must?
Yeah, have you read my email of yesterday
Not really.
about your recent changes? Okay, Bob Briscoe, yeah. There's a statement in there that if you like, the data sender, the one that's receiving the
Yeah.
ACK, must have the implementation to be able to parse an option,
Yeah.
even though it's only a should to send an option.
Yeah.
Yeah. So that if one end has implemented it, the other end can use it. I think that's okay with you, isn't it? Because
It might be okay, but
because I thought your problem was that you didn't want all the complexity of having to deal with sort of the failure of the option, and that's to do with sending it. But if you do get it through from the receiving end, you ought to.
So I mean, like,
work
I think
protocol.
it's correct to say, and I'm not sure what the exact wording is. I think it's correct to say you have to have the implementation to be able to pass it. If you add another kind of switch to say it's implemented, but I already know I don't need this information, so you don't have to pass it. That's like an implementation decision only, right?
it would be nicer if you made it a should, because then it leaves it up to the implementation.
So, but I mean, like, this is part of the TCP stack, and it's a generic protocol. So if you don't even provide the code to ever pass the option, that's not what we want, I think. If you have a specific connection where you know that you don't need to read the option, that's something else.
Okay. I think we can take this further on the mailing list.
No, I look up the exact wording and make sure it's clear. Definitely.
Yeah, I suggested wording in this email yesterday.
Yes, okay.
We had a problem like this with the SAC RFC, actually, that the negotiation wasn't ambiguous, and somebody shipped an implementation that would say, will SAC, and then never said SAC'd. And so, in fact, the actual negotiation in the code is will SAC indicates that you can receive SAC. I've forgotten the detail, but we don't actually turn on SAC until you see a SAC option, because there were half implementations that were fielded.
So basically you say, be careful and be very clear about it, right? Yeah. Got it.
I think like overall it would be nicer if an implementation could just choose to do the whole implementation without having to deal with the option. It would be nicer to leave that open in the RFC.
So I mean, like, what's your use case here? Because like I understand that, for example, in a data center scenario, you don't want the option, but if you have the code in your implementation, because you use a standard implementation that hopefully already has the code, and you never use the code, you never run through that code path, is that a problem for you?
No, I think it's more about not having to implement fallback and all that complex logic once you implement the option. So you can't just implement the option and not do dealing with all the problems that result from it.
So, but then your scenario is basically you don't use a general purpose operating system that has implemented accurate ECN for all use cases, and you actually customize it for your use case, right? Is that really what you have in mind?
I'm saying that the negotiation part and the part that you can get some feedback from the network without having to implement the option is still a viable option for an implementation.
But Bob Briscoe again, I don't see the problem with, I mean, obviously there's work doing the implementation, but if you parse an incoming option, you don't have to have any of the code that does any of the fallback, because you're not sending an options, and all the fallback is to do with sending it, not, yeah?
Yeah, that's a fair point. I think if it's only about parsing on receive, then it's fair.
Okay, I come back to you.
Any other comments? So I guess there needs to be a revision. And
Then we start last call.
I think we would like to see at least one more review on the document from someone.
Somebody volunteered already.
Pardon?
We had quite,
Praveen actually
Oh, okay. Yeah. So
should have a look at
Yeah, we had quite some reviews.
Yeah, okay. So when we have another one, then and the issues are addressed, then we can go to a working group last now.
Okay, thank you.
So RAG is next.
Hi everyone, I'm Yu Chom. I'm here to present the draft update for RAG. This is the third update. This is work done with my colleague Neil, Nandita, and Priya at Google. Next, please. So just a quick snapshot of RAG. In a sort of nutshell, RAG is, you can imagine that having a timer on every packet you have sent instead of just one timer. And then basically this timer is updated as you get an ACK and you get a better idea of the RTT, and you use that to determine and adjust the timeout for every packet. This is sort of a best way to picture what RAG is doing. Like the example on the right is simply showing, let's say you send 2 packets. So the second packet gets an ACK or SAC. So you get an update of the RTT. And then you just wind up the timer for the first packet. And based on the most recent RTT you get, you can sort of put an RTT plus some window to deal with reordering. And that's all like implementation detail and configuration details, but that's the basic concept of RAG. So doing time-based instead of counting dewbacks. Next, please. Another sort of combined feature with RAG is called the tail loss probe. And the problem to deal with is that today when you have a tail loss, you have to wait for a timeout. And tail loss is extremely common on especially short connections. Let's say you send 2 packets, both get lost. And here your C-win might be 100, but you only have 2 packets or 3 packets to send, and all of them lost. And then you reduce C-win to 1 according to the RC. And which is like a big penalty because literally you send 3 packets and the last 2 get lost. So you take a timeout. The tail loss idea is that, okay, on this kind of occasion, you can just, after a round trip or 2, retransmit a probe packet. What we do here is you simply retransmit the last one. And if that last one is quickly act within an RTT, then you say, it's really just like fast recovery. There's really not that many packet loss because, you know, things are sort of coming back. It's not like the entire flight is lost for a long time. So you perform a fast recovery instead of like a full timeout reset C-win style. So that's sort of the tail loss probe idea. And that works great with RAG because it's with all this timeout based recovery, you can just use this probe's RTT to adjust the timeout of the other lost packet. Next, please. So that's the basic idea of RAG. And in this IETF, we had just uploaded the third revision, which we add a few things. One is, I talk about the reordering window. Basically, when you wait for, how long do we wait before you declare a packet's lost? You can't just wait for an RTT, that's too aggressive. So you add some cushion, and that cushion, what we call is the reordering window. You say, all right, usually they might be reordering, so I wait for something. And in the past, it's a static value. In the new draft, we make it dynamic. And another thing that's new is called the dewback threshold mode, which now RAG can be like almost identical like the dewback thresh approach. And that offers something like a compatible mode for stack who want to deploy RAG, but also want to base on some kind of dewback threshold approach. And also there is a example of a fast implementation and like congestion control interactions that some people on the list has make a very good observation that RAG can interact with congestion control badly. I'll talk about details later. And in terms of deployment, in the Google server kernel, we have completely sort of replaced all the dewback threshold approach with RAG. So today, In our server production kernel, there is rack TLP and the standard timeout mechanism, which is required. But that's it. You don't see other like a FAC or 3 back or yada yada. There are quite a few. This is completely subsumed. Next, please. So what is this dynamic reordering window? So in the previous draft, the reordering window is simply set to 1/4 of RTT. Very, very simple. Deals with most of the losses, reordering, because a lot of reordering that we are seeing is just a very small scale. Let's say, the packet that you sent in the next is delivered just a little bit quicker than the packet that you sent earlier. So the reordering degree is small. But there are cases when the reordering window can get pretty large, especially on Wi-Fi links, where it's the Wi-Fi retransmission that causes the reordering, and the Wi-Fi link retransmission is highly dependent on the channel status. And in this case, rack will perform a spurious loss detection. You say, okay, this packet timer has fired and this packet should be considered lost. So if you use loss-based congestion control, then it's gonna take a hit on that. And in this case, initial idea we have is, all right, let's precisely measure the reordering degree. But it turns out to be really complex, because when you want to do that, you kind of have to remember the per packet timestamps, even when the packet has been acknowledged, right? So usually in TCP stack, when a packet is acknowledged, you free the packet because it's been delivered. In this case, you have to keep those extra state. Simply to do this precisely, and we believe that's not really worth the effort. What we do is we look at this option that has been created a long time ago called duplicate SAC. And what it does is when you receive a packet that covers a sequence that you have already received, you simply return the SAC option, says, hey, I got this duplicated sequence. And it has been implemented in all the major stacks like Linux, iOS, and Windows, and it's all on by default. And that's a great indication because it signals spurious retransmission. Jana, you have a question?
Yeah, clarification question. Why do you need to remember the per packet's timestamp after the packet is acknowledged?
Because even after it's ACK, right, you are trying to gauge, okay, this packet has been ACK, and there is some more packet that's been sort of in flight. And the way you measure the reordering degree is you have to measure the two.
Right.
Yeah. So that's why you have to keep.
No, I get that, but you would discard everything only after everything is cumulatively acknowledged up until that point. Right?
That's right. Yeah. So sorry, I think I made a mistake. It's not the ACT, it's the SACT. So
that's fine.
Let me clarify. Yeah.
Okay, that explains it.
Yeah.
Carry on.
All right, go ahead.
Just get to the end of the slide and then I'll ask the question.
Okay, yeah. So the basic idea is we use DSAC as a signal for a spurious retransmission, and we increase the reordering window when you get some of that, and you decrease when you are doing loss recovery when you don't observe further DSACs. It's a very simple one. Next slide.
All right, so can I?
Yep.
State your name.
It's Bob Briscoe again. What I don't understand is you're saying what you do, but not why you do it. Or what's your objective? Are you trying to get no spurious transmissions, or are you trying to get sort of,
Yeah. So great. So the objective here is to say you want to adjust this sort of reordering window, essentially the timeout for the packets, to accommodate higher degree of reordering. So if two packets are being reordered more than a quarter of minimum RTT, then today the previous version couldn't catch that, and it will cause a spurious sort of loss recovery.
Yeah, but what I'm asking is, how important is it to you not to have that? In other words, if you get some spurious retransmissions, do you care? In other words, what's your objective between that trade-off? Because that depends what algorithm.
Yeah, so again, if you use a loss-based congestion control,
Yeah.
It's basically if you also don't support TCP IFAIL, which is the TCP undo mechanism,
Yeah.
then you will see the, say Reno keep dipping the congestion window because of reordering.
Yeah.
Yeah.
No, I know, I
Yeah.
know that. I'm just saying that trying to completely remove spurious transmissions is impossible. So what's your trade-off? Do you see what I mean? It's maybe you can explain it better than me.
I have an answer to that, and that is if you take your favorite very, very, very complicated recovery scenario, and then insert in the forward path something that shuffles every 4 packets. Does it still work? And the answer is no, because you can't do the logic in sequence space. You want to do the logic in time space. And so the sort of the limiting case is allow every packet to have an independent delay. Okay, but so you're correct that there isn't specified a reordering threshold or an implicit reordering threshold, but you want to be able to design them independently. You don't want the algorithm to have built into it assumptions about how much reordering, what is the upper bound on the amount of reordering or the reordering distance. And so making the algorithm support arbitrary levels of reordering, such that you can then put in a policy and optimization about how much reordering and how much spurious retransmission you're willing to deal with.
And that's important, because the problem I see with adapting to the level of reordering you find is that networks will just cause more reordering, and then you'll adapt to more. Well, it depends how much, whether it goes beyond a round trip time.
Yeah. So the next slide I'll put more detail, but basically the idea is to accommodate reordering up to an RTT. Further than that, RAC couldn't do it, because in the end of the day, if you have 2 paths, one send it to over the moon and one is a local network, there is no way we can accommodate reordering like that. Yeah.
Praveen, Microsoft. So I wanted to know kind of which scenario led you down this path. Did you actually see reordering practically in cases where RTD/4 was not good enough?
Oh yeah, this is actually triggered by when I study the traces. I have seen reordering.
In particular environments or like Wi-Fi, or is this more general?
It's hard for me. This is server-side trace, so I don't know. All I know is it's on a Comcast, network, ASN. Yeah, but I've seen severe reordering on that.
I'm going to go back to my question and feel free to. Jana Iyengar, sorry. I'm going to go back to the question I was asking, and I'm happy to talk to you afterwards if it's not clear. You said that the correction there was after the packet is sacked. In that case, it's not deallocated in the stack. It's only deallocated after the packet is cumulatively acknowledged.
Yeah, so I think I give a bad.
Yeah,
so forget what I said.
Later.
I need to modify the slide. This is about what happened is that in the TSO processing, when you say you have, let's say packet 7, 8, 9 that gets sacked, right? In Linux, they will be collapsed into one sort of a packet buffer, if you call that. Yeah. Which you will lose the timestamps of individual packets. I see.
The timestamps are collapsed and lost. Okay.
Yeah, and then then you have to keep extra timestamp when they are doing the collapsing, and that's a very complicated change.
Got it. That makes sense. Thank you.
Yeah. Next slide, please. So this is the more detail of this dynamic reordering window. So all the reordering window still the initial state is a quarter of min RTT. And for every round trip that you observe some DSAC option, you just increment by a step. Essentially, you by another quarter of min RTT. It's important that you don't increase that for every DSAC, because you could get a lot of DSAC during reordering in a round trip. So we only do that incrementally. And again, this could still miss that, right? Let's say the reordering degree is actually 3/4 of RTT. So for the next round trip, you're still going to cause some spurious retransmission, and then you just have to learn again. So it takes some round trips to adapt to a level that's can accommodate the current reordering. And then we don't want to keep this high reordering for forever, because the problem is then your timeout gets too long. And if there is no reordering, you don't want to delay your fast recovery that long. So what we do is another heuristic to say, if after 16 magic number, 16 lost recoveries, and we see all the recoveries are done without seeing further defects, then we just reset it and just repeat this process. And all this design is, there is a lot of ways to make it more fancier, more adaptive, but we just trying to make it simple and good enough in our test cases. And then during fast recovery, we will temporarily reset the reordering window to 0 to be very prompt in fast retransmit. So the idea is to be conservative in the beginning, but once we decided, okay, we need to go into loss recovery, then we are very aggressive in marking the packets. We could have caused a lot of spurious retransmission, but with that decision, but it's sort of a trade-off that we have to make. And again, all this reordering window will be kept under the smooth RTT. So any reordering further than that, we cannot catch that. You will cause spurious retransmission. But I would argue that for any kind of case that to deal with reordering, there it's you cannot do that perfectly, like Bob mentioned. Next slide, please. So this is just a showcase of the two algorithms. You know, on the right, on the left, it's the old one, and on the right, it's the new one. Where this is not a this is in emulation, where we deliberately reorder packets to hell. And the sacks are in the purple color. You can see we are triggering a ton of sacks, including the D-sacks. And in the old version, it will just keep trigger all this false recovery. So you will see the throughput is only 60 megabits per second. But in the new one, you will see initially we're still not ramping up very good, but we are learning and increasing the reordering window. And once the reordering window is big enough to accommodate the reordering, then you don't cause further spurious retransmission. And even under severe reordering, you can zoom up your speed very quickly. So this is just to show that how this dynamic reordering window works under very severe reordering. And if on the right-hand side, the new one, if I look at a longer time scale, you will see after a while, essentially the reordering window will rewind, and then you will cause some spurious retransmit, but you will relearn and then pick up again. Next slide, please. So the last thing is the dewback threshold emulation mode. Dewback threshold can still be very useful, especially in ultra-low RTTs. Why is that? Because in rack, I talk about a timeout for every packet, right? But in, say, data centers, the RTT is less than 100 microseconds a lot of time. But your stack timer tick might be much bigger than that, say 1 millisecond or even 10 milliseconds. So in this case, let's say your reordering timeout is 3 RTT, 300 microseconds. The fastest timer you can fire is, say, a millisecond. Then that will cause some delay. So in this case, the counting, simply counting the dewbacks does offer a good advantage. And we can easily support that by saying, if the number of dewback threshold is bigger than or equal to 3, then just set the reordering window to 0. There is some very subtle differences if you want to be pedantic about how this dewback threshold is sort of triggered or used. Because in the RC 6675 says that in order for a packet to be considered lost, you need to have at least 3 packets that have been sacked with higher sequence. But for rack, it's not such a stringent, strict requirement. You just need to have 3 dewbacks and at least one of them having higher sequence. There's this example, you send 10 packets and packets 357 are sacked. In the standard RC, only 1 and 2 will be considered lost. But in rack, all the lost ones until the highest sack point will consider lost. Which one is better? I think it's really like a minimal. It's not worth like diving into all these details because, yeah, it's dewback threshold, which I find that a lot of implementation don't quite follow the RC exactly anyways.
So this is Rich Jeffnick, NetApp. Is that statement actually true? I mean, I was under the impression that in the example with RC 6675, you would enter loss recovery after the SAC of packet 7, but once you're in loss recovery, the entire point of 6675 was to recover all these 4 packets, right?
No, if you read the RC very, very carefully, it does say that you need at least 3 higher SAC sequence packets to trigger the do-back threshold. Yeah, I can point you. It's like 1 sentence if you are like.
This is Yoshi from Mike. And then about the 6675, you are right. 2 packet has been considered as a loss. But if there is any window size, we can send the packet 6 because we, in order to probe, this might be a loss, but we're not sure. But we can send it just in case, and then we can get feedback from.
Yes, you're absolutely right. I didn't put even the second if condition because we're getting into really super minor, subtle details. But yeah, you're right. It's possible there is an optional mode in the RC to trigger. Yeah.
I think that this exact example that you give was the behavior of 3417, so the old SAC recovery, and I believe that was the way that we wanted to address in 6675.
Okay, but this is again it's an optional mode. It's not like in the standard. I think we can take it offline and we can look at this, RC line by line and determine what exactly is the right algorithm. Yeah.
Jana Iyengar, what's the intuition here for considering 6 as lost?
Why don't you think 6 is lost when 3, 5, 7 are lost? It could be reordered. There is always possibility.
That's usually the argument, right? The only reason that 6675 or any of the RFCs have the 3 do-back threshold is for reordering. And that's why you also have the reordering window. If you remove the reordering window and you remove the 3 do-back threshold for 6, then you could very likely be marking 6 as lost too early.
You could, yeah. But again, in my experience, you either have, most of the time, you either have losses on all this sequence or there is some reorder, there is no loss. So do you always need to wait for more do-backs or SACs to confirm? I think it's really, yeah.
So this seems, I mean, again, I'm a little uncertain about, I'm not pushing back. I'm just trying to understand what the intuition here is, because this seems like early retransmit is getting folded in a strange way. Because early retransmit tries to do exactly that, right? If 7 was the last packet that was sent, then early retransmit would fire a recovery of 6.
Early retransmit wouldn't apply here because it requires in-flight size of 4 or less. Yeah.
That's correct.
Yeah.
But I'm saying that if 7 was the last packet that was sent, then that is what would happen.
So if you don't use this do-back threshold mode in this packet sequence, the pure rack without this mode will indeed arm a timer instead of retransmitting it on the 3rd packet. Yeah.
Right. It just seems more natural to me to mark 1, 2, and 4 as lost, but not 6, because there are more acts that are on their way back. 8, 9, and 10 haven't been acknowledged.
You are arguing if do-back threshold should be 1 on some cases. I cannot disagree.
But I guess that's the.
But in the end, it's a magic number.
No, but I think it's worth pointing out then that the do-back threshold here for 6 is in fact 1, because that's what's happening here, right?
Yeah. Okay. I think we are getting into the very well-defined do-back threshold. It's very different than what it was written long time ago in the very first, because back then there is not even SAC. Yeah.
Sure. That's fine. I just think that the spirit of what you're reading there as 6675 to me is accurate, and that actually captures the intuition of what I think about as the reordering threshold, and that's what I was trying to point out.
Okay. Next slide, please. So the last one is interaction with congestion control. There is the case when on a single act, when we receive it, we'll update the RTT, and rack can trigger a lot of packet that's considered it lost. The simplest case is, let's say you send 100 packet, right? Only the very last one made it. And in this case, rack will get an update of the RTT, and for packet 1 to 99, it's going to arm a timer, right? Once that timer fired, let's say after a quarter of RTT later, it's going to mark 1 to 99 packet lost. So the inflight will come from 100 down to essentially 0, from 99 to 0. So that's a big change of the inflight. And if you just implement the current renal congestion control, which always sent on fast recovery, first it reduces the C1 by half, let's say 50, right? So C1 is 50 or SS threshold is 50, and the inflight is essentially 0. So what you do is you burst 50 packets out. And without pacing, is very likely to induce another round of loss, which you have to spend to recover. So Linux doesn't have this problem because it uses this proportional rate reduction, which what it does is that during the fast recovery, you either do packet conservation. For every packet sacked, you send 1 more packet out, or you do slow start. For every packet sacked, you send 2 packets out. So it doesn't have this situation. So we would recommend using this fast recovery approach, proportional rate reduction, when you implement rack. Another helpful one is you can do TCP pacing so that you don't send the big burst. That would be the most convenient solution for a lot of other situations too. Next, please. So the development of rack is near the end. We don't plan any further sort of algorithm changes. Of course, little tunings is always possible. And Linux, BSD, and Windows all support that. I think the 4 authors consider rack's the latest draft is fairly complete, and we would like to ask for like a final review and maybe a last call if the chairs and the group feels it's ready.
Okay, thank you. One clarification question. You say Linux, FreeBSD, and Windows support rack. So I understood that Linux supports version 3 of this document. As far as I get, FreeBSD might support version 2, but not version 3. Is that right? Yep. And Windows?
Praveen, Microsoft, we support actually draft 1, not 2 or 3. So we don't actually support the 3 extensions that were added later.
So you support the dynamic stuff?
No.
No. Version 2?
Version 2, yeah.
Yeah, okay.
I think it was version 1, but
yeah, okay, but not this
into,
version.
Not this version.
Okay, thank you.
Michael Wesser, I may be asking something very strange because this isn't, I don't know. So the thing is, I've been playing with a variant of this, and that is really not quite the same. It's a bit more drastic in a certain way, but just something that I experienced, and I'm just wondering if the same thing could happen here, but I probably not, but I'm just wondering, so let me ask. Something I experienced is that with the logic of using time to decide what has been lost and what hasn't been lost, well, there were cases where I ended up terminating recovery and I was basically over and had just retransmitted everything, but I was lost. I was left with a large window that I'm now able to basically burst out immediately. So what I needed to create is a phase of pacing that is after recovery. I don't know if that sort of thing can happen to you, because I think proportional rate reduction would operate within recovery. So I don't know if you need to have something at the end of recovery where you can be, because basically the ACK clocking always allows you to send out another packet, so you keep the ACK clock and you spend your window. Yeah. But if you don't, then you may be left with a large window at the end of recovery. And I mean, it happened in my case, but that's really not exactly the same thing, right? So I don't know.
So I definitely agree your observation, because we see the same thing. That's why we recommend using FQ pacing for basically in general. Don't just do that. But for the PRR, it's really for just the fast recovery. But again, TCP is inclined to cause burst because of the C-wind in-flight differences. And this is sort of out of scope of the loss recovery. It's not just after the recovery, right? Let's say your C-wind is 100 and now you have 100 packets that you want to send. You burst them out. It's a general problem in TCP, not specifically applied to only.
I guess, I mean, that depends on how quickly you pace out stuff during recovery. So if you haven't been fast enough in sending out stuff during recovery, you have this credit after recovery. So if you're not sending out new packets, right, quickly enough, then you may be repairing your losses and all the losses are finished and everything is fine. But you have this credit of packets that you're still allowed to send after recovery
I'm
is
not
over.
sure because according to the congestion control RC, after recovery, your C-wind is always SS thresh, right? That's the standard.
Yeah, sure.
Yeah. And then, yes, you may not have much to send, so you will later cause a burst.
Yeah, but I mean, if C-wind is then much bigger than what you have sent, right? I mean, it may allow you to send out a large number of packets at the end.
It may, but I don't know why this is tied to loss recovery or just.
It is tied to loss recovery because if you're not sending during loss recovery fast enough, then you have not spent your C-wind, right? So if you're sending too slowly during that, then you don't have. I mean, it depends on how many packets you assume are in flight. So if you don't have.
So no matter you use rack or not during loss recovery, once the lost packet have been repaired, C-wind is always set to the SS thresh, and the in-flight is also not affected by the whatever algorithm you use. So I guess I don't.
Okay.
It seems like this is
either way. This is.
Of
I started out saying this is something I saw, and it's probably not even related to this. So
okay.
Leave it at that.
Praveen, Microsoft. So this recommends that we keep timestamps per packet sent, right?
That's right.
In our implementation, we actually chose to keep it per sequence number space because, for example, if you do like a TSO or LSO, then it's a group of packets that are transmitted at pretty much the same time. So there's some implementation efficiency gained by tracking this per sequence space rather than per packet, which also means that we can't track the original packet and the retransmission separately. And the other thing I found is that there is one case that you talk about tail drop, which will not be triggered if an implementation chooses to do this based on sequence numbers. It might be useful to comment on this in the draft, I think.
I think the draft already, that's exactly why we put TOP there. Because in the end, rack recent ACK still requires some ACK, right? And so for tail drops where you don't get any ACK, there is just nothing you can do in using these timestamps. You will have to send something to trigger an ACK to sort of cause more recovery actions. So it doesn't matter how you put the timestamp in a sequence space or in a packet boundaries. Yeah.
Okay. Another question. So you talked about the interaction with congestion control, and then you said Linux uses PRR to make sure that it doesn't blast the entire set of in-flight packets again. Is this just about making sure that you're only inflating in-flight by the sacked packets? Is that the part of PRR that is implemented, or there are other portions of PRR that are applicable? Is that, or is that just that part?
No, so it's PRR is not just that part.
Yeah.
But part of this idea of PRR is instead of bursting packets out, you want to do this you want to pace packets out and gradually reduce the congestion window instead of reduce it at instant and then cost burst. Yeah.
But my question is like the safety property would be just obtained by doing the correct inflation of the congestion window, right? The pacing is an optional part. Because today, for example, without pacing, like, the conventional loss recovery similarly inflates the congestion window. So as long as we guarantee that safety property, then the other portions of PR are not really needed for RAC.
So what I'm saying is that you can use either one of the two. Linux use both. It's kind of like a belt and suspenders, but during fast recovery. But if you already have pacing, then you don't need to implement PRR.
Okay, thank you.
Yeah.
Okay, so I would say give the implementers a bit of time to catch up with version 03.
Okay.
So hoping that whoever has implemented version 02 has interest in version 03 can report whether it works, whether it's implementable in a good way, or if they have any comments. So get some feedback before starting a working group last call on that.
Sure. Sounds good to me.
Yeah. Bob Briscoe. I'm wondering whether this draft, whether what you're trying to do is standardize the algorithm you have thought of, or whether you're trying to standardize, allow people to use different algorithms, and you need to describe what you were trying to do as a sort of black box. Do you see what I mean? Because
it's the former, essentially.
Right.
Yeah.
Okay. So it's documenting one algorithm.
That's right.
Rather than
yeah.
Okay.
It does not prevent other better algorithms.
Yeah.
Yeah. Obviously.
Okay.
Yeah.
Right. Okay. That you might want to say that, and I think the draft would benefit from having what the algorithm is trying to do, not just what the algorithm is.
Can you repeat that again?
What the algorithm is trying to do, not just what the algorithm is. In other words, what are the objectives?
You mean to put more explicit wording in the document in like?
No, not warning. Just you've just made it like reading a user manual about something that says this button does this button does this button does this, but you haven't said what the machine is trying to do as a whole.
Okay, this is a draft update, so I'm presenting the diff.
The whole draft doesn't say what it's aiming to do. What point it's aiming to reach.
Okay.
Yeah.
How about that? Can we sort of in offline figure out what wording you would like to change so that we can make it more clear?
Okay. I'm just trying to think of other people who might want to come up with different algorithms. In a standards body, we also need to agree what is a good aim for all of us, not just what is one algorithm to meet that aim. Do you see what I mean? Yeah.
I see. So you're saying there should be some consensus of the goal.
Yeah.
So this algorithm is just one approach toward that goal.
Yeah.
I'm closing the line after Jana, and I'm asking you to be quick.
Praveen, Microsoft. Sorry, one more question. So you said that the Linux implementation is your implementation has replaced all of the other loss recovery with RAC. Is it a goal for the draft or the RFC to say that an implementation should do that, or are you going to leave that open for implementations to do both if they chose to do so?
To do both?
Yeah, I mean, DUPAC thresh as well as time-based.
Yes, we recommend that you do enable this as a backward compatibility, right? Yeah.
Jana, a very quick suggestion that this is a working group document, so I think you should take input from people who have specific suggestions about motivating text and so on. Specifically speaking to Bob. Bob, you write very well. I think it'd be wonderful to actually have what you're suggesting, but I would also say, suggest text.
Yeah, so I think I already mentioned that we'll work offline to improve the document. Yeah. Okay.
Thank you. Yeah. Okay, so where are the blue sheets? And has everyone signed it? So if not, please catch one and do that. So the next one is the TCP converter. This will be fun because
movie PowerPoint. How do I do a PowerPoint presentation?
I don't. Tell me where to click.
Yeah,
This
this
one.
one.
This one.
This one? This one.
Okay, so this presentation is both the first presentation of the converter draft in front of TCPM, because it was already presented in MPTCP in Prague last year, but we did not have the opportunity to present in TCPM in Singapore, and then an update of the draft after the working group acceptance. So next slide, please. So the initial motivation from the converter comes from the work that has been done in MPTCP working group. And in MPTCP, we see that there are more MPTCP clients than MPTCP servers, and there is a benefit of using MPTCP in the access network to be able to combine different paths, even if the server does not support MPTCP, so that you can go to a converter that supports MPTCP, so that you can benefit from the two paths in the access network, even if the converter has not yet been upgraded to support MPTCP. Next slide, please. So what are the objectives of the TCP converter, which has now been accepted by the working group, is to aid the deployment of new TCP extensions. And if you look at the history of the different TCP extensions, we've seen that extensions are first deployed on the clients, and then they are deployed much later on the server side. And in enterprise networks and service provider networks, there is a possibility of deploying converters to aid the deployment of some TCP extensions. So the TCP converters, they act like proxies, and they will proxy connection initiated by clients. And the objective of the converter draft is to do this proxy without requiring additional RTTs. And one important point of the converter draft compared to other solutions is that the converter has the ability to inform the client of the options that are supported by the server, so that the client can detect if the server supports MPTCP, for example, then it can decide to bypass the converter. So it means that you only use a converter when there is a benefit of using the converter. Next slide. So just simple use case, if you want to do MPTCP in the access network from a smartphone to a server that does not support MPTCP, you just use MPTCP to the converter that acts as a TCP proxy, and then you have a regular TCP connection to the final server. Next slide. Next slide. Next again. So what are the basic principles for the converter? So it's an explicit TCP proxy between the client and the final server. So the client knows the IP address of the TCP proxy. The client will send comments inside the TCP byte stream. So you can see that as an evolution of SOCKS, for example, or refinement of SOCKS. And to be able to achieve zero RTT, we just put the comments of the proxy in the SYN and during the initial handshake. And the comments and response are encoded in TLB format to simplify the parsing and the processing of the options. And there is a way for the converter to inform the client of the TCP options that are supported by the server to enable it to bypass the converter if the server supports the required extensions. Next slide. So now I have a set of examples to show you in principle how it works. And the schema, in all the figures, you will see there are three colors. The green color corresponds to the IP addresses. The blue colors corresponds to the TCP header, including the TCP options. And the red color is the information which is added by the converter protocol. And this is part of the byte stream. And this is encoded as a set of TLVs. So let's do an example. So the client wants to reach the server. To be able to reach the server, what the client will do is that it will send a SYN with a TFO option to the converter, and we use the TFO option to be able to put data inside the SYN, and the data that we put inside the SYN is the IP address and the port number of the final server. So the converter receives the SYN, and thanks to the TFO cookie that it has provided to the client, it confirms that the SYN is legitimate. And what it will do is that it will initiate a connection, next slide please, towards the server, and it knows the IP address of the server from the connect TLV, which was part of the original SYN. Then the final server will reply to the SYN with a SYNACK, next slide please. And so the connection from the converter to the server is now established, and the converter, next slide please, will confirm with a SYNACK that the connection to the client has been established. So with the connect TLV, we pass the information of the final destination to the converter.
Hi, Olivier. Lars, I got a quick question. You stick the IP address into the payload, not the DNS name?
In the current version, this is the IP address because we want the converter to be fast. And if we put the DNS name in the TLV, then it means that we have to do DNS resolution in the converter.
Yeah, so I'm sort of worried about or thinking about scenarios where the client's DNS resolution might be limited and the proxies might not be. So just if you thought about it, that's
a possibility to add the new TLV where you put a DNS name instead of an IP address. In the current version, it's only an IP address because we want to be fast on the converter side. Next slide. So, as I said, one of the benefits of the converter is that you can detect whether the final destination supports a given option. So let me take an example with MPTCP, but it would work with other TCP option. So the client creates a connection request through the converter and here we are using MP capable option, which is shown as MPC, and we are using the RFC 6824 bis, so just MP capable without a key to the converter. Next slide, the converter will try to establish an MPTCP connection to the server. The server is MPTCP enabled, so next slide, it will reply with the MP capable option and with the key which is selected by the server. And what the converter will do is that upon reception of the SYN plus ACK, what it will do is that it will extract the TCP option that have been returned by the server, and it will send them in the payload of the SYN plus ACK, next slide please, to the client. So that the client, by just parsing the TLV, which is part of the byte stream of the TCP connection from the converter to the client, will know that the server supports MPTCP, and knowing that the server supports MPTCP, then the client for the next connection can decide to bypass the converter and go directly to the server. So that's a generic way of enabling the clients to understand what are the options that are supported by a given server, and it means that you can bypass the converter for this specific destination. Next slide, please. So to be able to use TFO from the client to the converter, you need to be able to know what is the TFO cookie which belongs to the converter. And for that, there is a bootstrap connection. So when the client starts, it has to initiate a connection to the converter, just send a SYN with an empty TFO and a bootstrap TLV, and the converter will reply to the client, next slide, to indicate what is the TFO cookie that the client has to use to reach the converter, and what are the supported TCP extensions that the client supports and allows to do a conversion. So that's a way to learn the capabilities of the converter during the bootstrap procedure. Next slide. So now we know the converter cookie and we can use it in the client to reach a converter. So next slide. Yeah, next slide again. So what is the tricky part is how can you do TFO to reach a server while you are already using TFO to reach a converter? And the idea is that we have done the bootstrap. Since we have done the bootstrap, we know the cookie of the client, of the converter. So we use that in the TCP options, that's the blue color. So we use the cookie that we receive from the converter. And we want to obtain the cookie from the server. So inside the connect TLV that we put in the byte stream, in the establishment of the connection, we have a specific TLV that indicates that we want to send a TFO option, an empty TFO option to the server. So when the converter creates the connection to the server, what it will do is that it will send a SYN with the empty TFO option that comes from the connect TLV of the original SYN of the client. So the server now knows that the converter is trying to create a connection and request a TFO cookie. The server will reply with the TFO cookie. So this is the cookie which is assigned by the server. So this TFO cookie assigned by the server is returned to the converter. And what the converter will do is that, as with the MPTCP example, we will just take the TCP options that have been returned by the server, and these TCP options that have been returned by the server, we put them as TLV inside the SYN plus ACK, which is returned by the converter to the client. And the client can parse the TFO option, which is included in the byte stream. And from knowing the TFO option, which is included in the byte stream, it can detect what is the cookie, so SC, that has been provided by the server. And the client can cache this cookie for the specific server. Now on the next slide, we will see how the client can open a TFO connection to the server. So now that what it will do is that it will go through the converter, use the connect TLV, specify in the TCP option part the TFO which has been supplied by the server. So this TFO is copied by the converter in the SYN that it sent to the final server. Next slide. So you see the TFO which has been allocated by the server. The server recognizes the cookie that is provided to the IP address, which is the IP address of the converter, and it accepts the data. And then you can do the SYNAC, and the converter does the SYNAC as usual. So the solution works with TFO as well, just by using the information in the connect TLV. So next slide, please. So this was the introduction of the converter, and this is basically what I've shown in Prague last year. Now I will try to describe what we have done since the working group adoption, which was 3 or 4 weeks ago. So we did lots of small editorial changes to try to clarify and simplify the text, and we have looked at how other TCP extensions than TFO and MPTCP could be supported by the converter. So next slide, please. So first, we look at the what we would say the base TCP options, so the options that are part of RFC 793. So end of option list, no operation, and maximum segment size. For these options, we don't see any benefit of doing the conversion of these options on the converter. So what we propose is that the converter does not provide the conversion services for these kind of options. Next slide. Then there is window scale. So the window scale option is really a property of the TCP implementation. And in the converter, we have a TCP connection from the client to the converter and another TCP connection from the converter to the final server. It makes sense for the client to request the server to use the converter to use window scale, but we don't believe that it makes sense for the client to request a specific window scaling value for the converter. So the idea is that we don't want the client to be able to impose a specific window scaling on the converter. So this should be the property of the converter for that.
Are you familiar with the rounding hazards with the window scale option?
With? Sorry.
There's some hazards in the window scale option that you can't avoid retracting the window if you're close to the end of the window space, and the rounding is such that you can't specify the boundaries that the actual window you want to announce. I'll take it offline.
Okay.
There's some deep traps lurking here.
So next slide. Then we have timestamp selective acknowledgements and multipass TCP. We believe that for these options, they can be supported by the converter. So this is true for timestamp, for SAC permitted, and for multipass TCP. And of course, kind 5, the selective ACK option, it cannot be advertised in a SYN, so it doesn't make sense to support it on the converter. Next slide. Then fast open. So I explained how we can support fast open. So this is part of the design of the converter draft. Next slide. TCP user timeout. So there is an option which is related to TCP user timeout, kind 28. But it's unclear to us whether this option has really been implemented or not. So we know that the socket option is implemented, but we don't know whether the TCP option is implemented. So is someone aware of an implementation of the TCP option for the TCP user timeout? If you are aware, let me know, and then we can think on how to support it and whether it would be useful to support it. Next slide. Then there is the TCP authentication option. Well, the objective of this option is to be able to detect modifications to the TCP header and the TCP payload. This option is in principle against a proxy in the middle, so it does not make sense for a converter to be able to support TCP authentication option. Then the question is whether there is a benefit in trying to support the NAT extension of the TCP authentication option. And we'd be interested in having feedback from the working group on that. So my understanding is that the TCP authentication option is mainly used for BGP sessions. And for that use case, it doesn't really make sense to go through a proxy because you want to use a TCP option also to detect failures. And so it doesn't make sense to go through a proxy. And next slide. And then we have the experimental TCP extensions. This is the list which is registered by the IANA. In the current draft, we do not consider these experimental TCP extensions, and our suggestion is that those extensions should be described in a separate draft. Otherwise, we will have a draft that will need to be updated every time there is a new experimental TCP extension. Next slide. So to conclude, we started from a proposal that was focused on multipass TCP and TFO, because there is a clear demand to be able to support converters for multipass TCP. But the discussions within the IETF convinced us that there are other use cases for other TCP extension. So in the draft, we try to take into account all the comments that we have raised during the email discussions on the MPTCP and the TCPM mailing list. So we have an application level protocol. We still need to have a service name or a port to be reserved by IANA. So we use 0RTT through TFO, and the client can bypass the converter if server supports the extension. So our next steps will be to improve and fine-tune the discussion of the other TCP extensions based on the feedback from the working group. And we will get feedback from implementers and do interoperability tests. As far as I know, there are 3 implementations that are being developed for this solution.
Matt Mathis, I may have missed it, but has there been any discussion of how this interacts with TLS?
So what happens when you do TLS from the client to the server? So you have to rely on the certificates that are provided by the server. And so the server will authenticate the connection. And so you have, since you encrypt everything and you authenticate everything, passing through a proxy or passing through a router doesn't change anything, because the TLS is working at the byte stream layer and not at the TCP header. So the only issue are the IP addresses.
And handling the certificates.
And?
Handling the certificates.
Yeah, the certificates, yeah.
Yu-Chong Chen. I'm still find hard to convince myself about the motivation. Seems like the motivation slide is to support multi-pass inside the access network.
Yes.
But the most useful MPTCP feature usage I've seen is to do solve the parking lot problem, where you launch the use MPTCP across both Wi-Fi and LTE interface on your phone or cellular interface. It doesn't seem to match this case, because then where do you put the converter? It has to be very close to the server. So could you put more detail on some example scenarios of doing MPTCP inside an access network? What's the benefit? Like, what motivates them to do that?
So just one motivation, for example, if you look at what has been explained in Korea about the deployment and the usage of the SOX proxies in Korea to bond Wi-Fi and LTE together, there the use case is to put the proxy in the network operators itself. So you have a network operator that provides Wi-Fi and LTE services, and the proxy is inside the operator's network.
Okay, so essentially the access network is doing both Wi-Fi and cellular service. Yes. Okay, but that sounds, I feel it's very limited, at least doesn't apply to the case in US. Of course, maybe in Europe, but I don't know how many ISP are providing both services together, like they have a large user.
So how many ISPs are providing both Wi-Fi and LTE?
Yeah, and cellular services.
So if you are an incumbent operator, typically when you will have mobile services, and then if you have DSL, then you have Wi-Fi access point on your DSL network, and many networks are providing solutions such as phone or others to share the Wi-Fi access point from multiple users. So this is pretty common.
Okay. Is this part in the draft that what you just provide the example? The example you just provided?
No. So there are examples about, if you look at the draft on the use cases for MPTCP, those examples are in the RFC, I think it's 6041. that lists use cases and deployment experience with MPTCP.
Okay. Does the draft cite that RC?
I think yes.
Okay. Thank you.
Hi.
State your name.
Jonathan Looney. Sorry, I violate the height requirement, evidently. I had two comments. My first comment is that I found some tension in the draft between this idea that the client should be able to specify exactly which extensions it wants to use, and therefore the purpose of this is to enable them to use those extensions when they want to, at least up to the converter that supports them, versus the what seemed like much less control the client has over what the server or the converter talks to the server. It seemed like there was a lot of things where the draft says, well, the client can request something, but the actual values are dependent upon what the converter's stack supports. And it struck me that there was a real dichotomy between the fine-grained control you want to give the clients and the lack of control they have over that other TCP session. That's the first thing. I'll let you answer that, and then I have...
Yeah, so I see what you mean. So the draft comes from a solution to support MPTCP. And then we were asked to extend it to other TCP options. And what we need to do is that, but we did not have time during the working group acceptance, between the working group acceptance and the draft deadline, to look at all the TCP options in details and to see how the client can use each of the TCP options and to build a table with all the combinations that would make sense. But this is something that we plan to do. But the idea is that we want to let the converter specify, I would say, I support this TCP extension. Let's say I support MPTCP and SAC, and I'm able to do the conversion services for MPTCP and SAC. And then for timestamp, since I'm implementing 7323, I will do timestamp for all the TCP connections that I will open to the final destination anyway. And so this is not a conversion service. So there is a tussle between what the client is requesting and what is the basic policy of the converter TCP implementation. And this is something that we need to clearly specify in the draft. And this is related to your question, I guess.
Yeah. My second comment is that I think the draft really needs to explain why or how you're going to avoid all of the normal pitfalls that we see with middle boxes. I mean, you're essentially adding a middle box here. There's all sorts of inherent concerns with that. And I think that your draft really needs to explain how you're going to avoid all of those.
So we are aware of the issues with middle boxes because they played a key role in the design of MPTCP, and we had to pass through all of them with MPTCP, and we managed to pass through all of them with MPTCP. I think the difference between the existing middle boxes and the converter is that the converter is explicit, so you know what the converter will be doing to your TCP connection. And this is a major change compared to the middle boxes. And then we can add a section looking at if we have on the path a middle box that would remove TCP option. Here is what will happen. We can have a section saying if we have on the path a middle box that removes information in the SYN payload, this is what will happen, and so on.
I'm not sure that this really is different than a middle box, though. In some ways, it is different because you explicitly know it's there. In other ways, it's not different, and it doesn't solve all of the concerns that are there. Sure, it's not at that point, it's not transparent, and so you have maybe the problems are different, but there's still potentially problems that are there and concerns that are there. And so I still think that I still think there are considerations that should be addressed, and I'd be happy to talk more about that offline.
Yeah, but we can extend the middle box section. So there are two parts of the middle box section, the part between the client and the converter. I think this is the one where we should have the focus. And then there is the part of middle boxes that would sit between the converter and the final destination. but this is part of the existing TCP extensions for that. So I would focus on the client converter path and the presence of middle boxes on those paths. Do you agree with that? Or do you want to discuss as well what happens when you have middle boxes between the converter and the final destination?
No, what I'm concerned about is that when we see middle boxes, we have problems because the middle boxes can go stale. They may support slightly different versions of various drafts. You also have a buffering that occurs there that you need to deal with. People trying to measure with timestamps get different results. I mean, there's all sorts of things that occur at middle boxes, and you're introducing a middle box. Now, it's not a transparent middle box, but it's still a middle box, and there's still considerations that make us typically not like middle boxes being there. And you need to make sure that you address those as part of your draft and say how the converter is not going to cause those problems or how it's going to work around the problems that are inherent with middle boxes.
Yeah.
Yeah.
So if I have the proposal right in my head, then the big difference is that you're actually connecting to the converter. So the destination IP address is the destination IP address to the converter. You open an end-to-end TCP connection to the converter, which is really not the same as a middle box. So a lot of those considerations we're worried about really does not apply because it's an explicit thing the client decides to do.
Praveen, Microsoft. So I in your slides, you showed the success case where, a connection was successfully established. What about the error cases where, the server sends a reset back, or it might be doing like DDoS protection. It might be trying to validate the client's source address ownership.
Okay.
How would all those things work?
So what happens if the server refuses the connection that was trying to be established by the client through the converter? Then the server will send a reset to the converter, and the converter will relay the reset to the client.
So does it relay all TCP packets? Is this like converter trying to just relay all TCP flags, and is that what it's doing, or is it?
No. So we have two TCP connections. So there is one between the client and the converter, and one between the converter and the server. And so if the connection which is attempted by the converter to reach the server is refused by the server, then the converter will refuse the connection to the client. What we do is that the converter will only send the SYNAC once it has received the SYNAC from the server. Because we want the client to be in a position to be able to detect whether the server is accepting the connection or not.
Right. What about like source address validation for DDoS attack prevention? In that case, the server would challenge the original SYN. How does this get relayed?
How do you relay source address validation? What kind of source address validation do you want?
I mean, you might be doing like SYN auth, right? You might send a challenge ACK back, or you might drop the SYN to validate that the client actually.
So you drop the SYN?
Yeah.
And you ask the converter to retransmit the SYN?
Right.
But on the converter, you are trying to open a TCP connection to the server. And so there is a state on the converter that will retransmit the SYN, because you are attempting
this just seems like it will trip up all kinds of like DDoS protection algorithms, because now this one IP address is trying to open like so many connections on behalf of so many.
So on the slide, there is one IP address for the converter, one for the client, and one for the server. But the deployment could use a block of IP addresses on the converter and have one IP address which is directly mapped to each client. So it doesn't mean that all the connections will go through a single IP address from the converter.
Okay.
So the converter could have a block of IP addresses.
It would be good to clarify that in the draft if it's not already there.
Yeah.
Hey, Jake Holland. My concerns are similar to you, Chang's, I think. The draft says no, that configuring the list of converters in the clients is out of scope. I understand, but are there any configuration strategies that are known to work? Like if you have for example, when the Wi-Fi is in one network and the LTE is in another, then the draft talks about the routing would be configured such that only certain client IPs would reach the converter, right? So when some of the paths are out of scope, but is the client able to tell, I guess, besides not seeing the SYNAC?
I'm not sure I understand what you mean. So you are discussing about deployment where the client has multiple paths to reach the converter?
Where the client has multiple paths and perhaps some of the paths do not reach the converter.
But if some of the paths do not reach the converter, then you are trying to open a TCP connection and you can apply something like API balls or whatever to detect which path is able to reach the converter, because the converter has an IP address. And so you can test whether a specific path will reach the given converter.
Okay, so this is just sort of the client's problem to determine whether it can reach
there is the bootstrap, which allows the client to try to open a connection to the server. If it has multiple paths, then it can try to do bootstrap in parallel over the different paths and to see which path reaches the server that it wants to interact, the converter that it wants to interact with. And once it has created the bootstrap to this converter, then it knows that this path is working to reach the converter.
Okay, so do you have a list of sort of expected characteristics of the discovery mechanism for the list of converters? Maybe?
What do you mean by expected characteristics?
I guess.
So we just validate the establishment of a TCP connection to the converter, and we get the TFO cookie of the converter.
Okay, I can take it off.
And we learn what are the capabilities of the converter.
And it's a kind of the same answer, Mia Kühlemann, by the way. So you have an IP address. So if your paths are connected to the internet, you should be able to reach the IP address. It's not like that the converter is somewhere on the path that you have to bypass. You actually explicitly send your traffic to the converter.
Right, but they said that it's configured to route, not all of the clients, specifically to avoid getting things that are not an appropriate path. Right?
So yeah, if you try to connect to the converter and the converter the converter decides it doesn't want to support you as a client, then it says like no TCP connection for you. You have to connect to the server directly, right?
My name's Tim Shepard. As people have been asking more questions, I get more confused about what exactly this is. And I think perhaps there's another part of the story in that you also need a converter that is inside the client operating system somewhere. I don't know whether it's in the kernel or in some library, but I was trying to imagine, does the app have to be reworked so that it knows to connect to this converter instead of connecting directly to the server?
It could. So it's just like SOCs. With SOCs, you have libraries that will implement SOCs, and there are applications that support SOCs.
Yeah, so
SOCs is a typical
example. This is much, yeah, so the person who, I forget who was asking, you have to talk about middle boxes. This one view of this is much more like a SOCs proxy.
Yeah, it's an optimized SOCs proxy.
And then somebody was asking about TLS earlier. It's sort of like if this connection is being initiated, the TLS would be between. You could also, there's two possible TLSs. There's a TLS session with the converter, and there's a TLS session with you might want a TLS session with the converter.
I don't think we want to have a TLS session to the converter, because we want the solution to operate on the TCP byte stream. And
but some of the payload of your session is actually communication with the converter, and you might I don't know if.
But only the beginning of the payload. So this will be stripped by the converter, and there is. So if you have if you do a TLS session, the TLS session will be with the final server.
So you're saying you would never want to secure the connection with the converter.
At this point in the draft, no.
Yeah, but anyway, but all of this was unclear to me, I guess, is my real point, as to what exactly you're talking about doing. And maybe it would help if I read the draft.
So looking at the TLS case, so the TLS case, when you create a TLS session, you know the IP address of the final server. In this case, you would have to change a bit the TLS implementation on the client to say that we reach this final server, which is part of the connect TLV via an explicit proxy.
And it would be I guess I'm speculating, it would be similar to doing a TLS session with some server out there on the net through a SOX.
Yeah.
So
Yeah,
your
the
actual
same
your connection to the SOX
Yeah.
gateway is one IP address, but the TLS session would understand that it's not actually, the TLS session is not with the same IP address that we're sending the packets to, or
Yes.
that we're opening the TCP connection to.
Yeah.
Yeah, so thanks for helping clarify that a little bit.
Beyond Metzdorf, Apple. I have a question in regards to the TFO converter functionality here. I would imagine that in a scenario where the access provider is deploying converters large scale, there will be many, many different converters, sort of like in a load balance scenario maybe. And I could imagine that the outgoing IP address from the converter to the actual server might be changing, in which case you might not get much benefit out of converting TFO because that relayed cookie won't be valid anymore.
It depends on how you will manage the IP addresses on the converter. But if you look at IPv6, for example, with IPv6, you could have a deterministic way of mapping the client address onto a converter address. And I think this solves your issue. And the other point is that with the bootstrap procedure, the client is able to connect to one specific converter. And so there is some stickiness in the relationship between the client and the converter. So you don't go through one converter or another from one TCP connection to another. You just, when you boot your client, you select one converter and you will stay with the same converter for some time.
For some time, but typically TFO cookie lifetime might be longer than some time. The converter could go out of business, could go into maintenance, and then you might have to select a different converter breaking TFO to the actual server. It's just a minor comment. It's not.
Yeah, but then when you go to maintenance, then you will detect that you are not to the same converter because your cookie to the converter will be refused by the converter. So you will know that all the cookies that you have learned, you have to, on the client side, you have to delete them because they are not valid anymore because you are not sure that you are using the same IP address to reach your final server. But this is part of the client implementation.
Yes, but not if the converter was a load balance converter that you don't know what you connect actually to. You still connect to the same IP address, which might be preferable.
Yeah, but then there are questions on how you want to deploy the converter and how you want to do load balancing for the converter. So you have to take special care because this is not a standard web server. This is something else.
Okay.
Yu Chang Chen. I think it would be really helpful in the draft to have sort of a walkthrough of the process. Let's say a mobile phone client trying to use this feature and wants to go to https youtube.com. How does he get the converter address and how does he initiate those connections? And I think that will help a lot of this sort of related problem of middle boxes and deployment schemes. Because right now we're trying to infer that based on what you presented, and that's why you get so many questions around that. Yeah.
So we can write this as an appendix, but there are multiple deployments that are possible. So we can find an example where, for example, you would have a DNS name that corresponds to the converter, but this is not the only possible deployment. And so we can just provide that as an example, but there are many deployments that are possible.
Yeah, I think an example will help, and then definitely you can say this is not the only way to use that, but it helps a lot to understand the scheme.
Thank you.
Hi, Ravi. Can I ask a clarification question? So since you are talking about implementation, so can we implement this everything on the user end, or do we have to modify TCP stack?
So the main issue is on the converter side. If you want to implement that solution, when we receive a SYN, we don't want the TCP stack to reply immediately with a SYNAC. So we want to delay the acceptance of the SYN until we have accepted the connection from the server side. So this is not totally a user space implementation. So you need to extract the scene, put it in a buffer while you are trying to open the connection to the server. And once the connection to the server has been confirmed, then you can put the scene back in the stack to confirm the establishment of the connection.
Okay. So then, so someone is working on implementation. So what kind of platform they are working
So there are 3 implementations that I'm aware of. And the plan is to discuss with the implementers and to try to do some interop tests before Montreal and get back in Montreal with results from interoperability tests.
Okay. Thank you.
So if there are no further comments, then thank you and continue the work. So the next one is Fernando doing this remotely, and it looks like he wants to use his screen. So let's try this.
So Fernando has to go to the...
Yeah. Fernando, I think you need to go to the mic if you hear me. Then we can accept you. Here he is.
Okay.
We see you and hear you.
Are you going to see the slides from my screen, or are you going to show them from your screen?
I can show them from my screen, and it would be nice if you could. You are very loud in this room.
If I could? Okay.
Calm down. Where's the sequence number stuff? What?
This one.
Ah, yeah.
Okay. Hello. This is going to be a very short presentation about a idea that we wrote with David Orman. Next slide, please. So I assume that you have read previous versions of this document. Essentially, if you look at 793, there's essentially a bug in the sequence number validation. Essentially, with the rules that we have in RFC 793, there are 3 scenarios that would actually fail. One of them is the TCP simultaneous open. The other is the TCP simultaneous close. And the other one is the case of simultaneous zero window proofs. Essentially, all of the stacks that we know of have fixed these issues like many years ago, but the relevant standard 793 was never updated in this respect. Next slide. So what's the goal of our document? Well, first of all, document the bug. Second, to propose a workaround for it. Third, to document other implemented workarounds, like we propose one of them, but for example, Linux differs from that one. And formally update 793. Next slide. So essentially, when it comes to the difference of what we propose versus what some other stacks have implemented, essentially with a simple change that we propose to 793, which is, for example, what has been implemented on BSDs for like tens of years. Essentially, we accommodate Windows proofs of 1 byte. Whereas in the case of Linux, they do like a more, let's say, more general test in which they allow for simultaneous zero windows proofs of any size, not just 1 byte. I mean, 1 byte is the de facto standard, but they accommodate like Windows zero window proofs of any size. Next slide. So essentially, well, we wonder what we should do with this document. A couple of years ago, when the last time that we had committed time on it, Some folks have argued that we should be documented what other stacks are doing. So far, our ID contains that. Our question to the working group is whether this should be adopted as a working group item, or what's the proposed way forward.
Any comments?
This particular bug, this is Matt Mathis, this particular group of bugs are in the category of things that cause me to be non-encouraging about any new implementers. That there's a lot of really important details in the implementation that are not written down. And getting them written down would be a major step forward and actually get a completely self-consistent description of the protocol itself.
Yuchong Chen, can we just merge that into the 793 bits?
So this is Michael speaking. That is certainly one option that we could discuss. However, formally, when we adopted 793 BIS, we actually decided that we will only adopt changes that have TCPM consensus, or even IETF consensus, to be precise. So we would violate our procedure. Having said this, it's certainly one option that we have. As far as I know, WES has at the moment an informational comment on this problem already in 793 BIS. But I mean, changing the equation, according to our previous consensus, we would actually need a standard struct specification for it. As I said, we can discuss what we do exactly. But if we would change 793 BIS in this respect, we would probably have special care specifically on this change, because we don't have the RFC for this specific thing.
So things like the way I understand the suggest sequence is, first we need to have consensus that this is indeed a problem we want to work on, and then decide whether to put in RFCs, the BIS or a new RFC.
Yeah, I mean, for sure, for 793 BIS, the most important thing would be to agree on if, other than acknowledging that there is a problem, if there's agreement on one solution, several solutions, and possibly on recommendations to implementers. Because it's already understood there's more than one solution to the problem. But the key question is do we know that there is a minimum solution for this? Or is the only thing we can do documenting a set of recommendations to implementers how to work around that bug? And that actually is something that this group has to decide.
So my question is, what's wrong with 1x0 window probe? I mean, that's the part I don't understand. Yeah.
It's not that it's wrong. The thing is that you could actually send Windows probes of any other size. So it's like the 1 byte window probe is a de facto standard, but nobody requests you or requires you for the 0 window probe to just be exactly 1 byte. You could do 0 window probes of 5 bytes if you wanted.
So you want to relax the current standard to allow that, or?
No. Actually, what we propose in our document is to accommodate this 0 window proofs of 1 byte. Okay. Now, when it comes to 0 window proofs, there's nothing that requires you that they have to be 1 byte. So what Linux did, which is not what we are necessarily recommended, is accommodate 0 window proofs of any size. That's not what we do in the document is just accommodate the case of a 1 byte 0 window proof, because that's the de facto standard. But Linux, they made it more general. I guess that they said, okay, well, if there's no requirement that those have to be 1 byte, then we should accommodate 0 Windows proofs of any size.
And that will cause some problems if Linux is doing that today?
No, at all.
Okay, I guess I'm not clear what problem are we trying to solve here other than improving the changing the RFC.
No, so you have a problem. The problem that we have now is that there are 3 scenarios that fail with the text that you have in 793. Those are simultaneous opens, simultaneous close, and simultaneous zero windows proofs. So that's the problem we are trying to solve. Now we have one proposed workaround for that, which solves all of those problems and accommodates zero windows proofs of 1 byte. Those are the de facto standard. Okay. Now Linux, when they fixed this problem, they made the fix more general, and they say, okay, we want to allow zero windows proofs of any size, not just 1 byte, which is the de facto standard.
Okay, now I understand the problem. I think I need more time to assess how important or serious these problems are. Yeah.
Michael Trickson as an individual, I think what this document is missing right now is documenting the solutions used by several operating systems. So you describe vaguely how Linux is doing it, but I think it's agreed it's a problem in the specification, but we don't know what all the implementations are doing. So I would suggest reach out a couple of implementations and document what they are doing. I'm willing to offer help for FreeBSD, but reach out also other ones and document this in this draft.
What we propose in our ID is what BSDs do. Actually, it might be David Borman himself that implemented the fix in BSD, but I might be wrong. But what we propose is what BSDs do.
So this is not stated in the document, and reach out other operating systems as well, so that we have that we can see what is out there. The other point is, I'm not sure, I'm not fluent in the RFCs, but my impression was that zero window probing is tied to 1 additional byte. You can't overbook by 10 MSS. So I don't know about that, but reach out implementation status.
Lars Eckert, so I think that fixing the bug in 793 is sort of a no-brainer, and we should do this. And whether that means that we do an errata against 793 after we do a request consensus, what should be in that errata, or if we put it in 793 bis, which will eventually obsolete 793, I don't really care, right? But I think fixing this is a good thing. I would also I think this is going towards what the previous speakers have said. It would be nice if whatever we did wouldn't render major stacks immediately out of compliance, because we are late here. They've all fixed this. So if we can write text that the documents what major stacks have already done and doesn't force them to change what they have been implementing for the last couple of years, that would be nice. So that means allowing certainly the 1 byte thing that the BSDs are doing, but maybe also permitting the multiple bytes thing that Linux has been doing. Not that Linux, frankly, would really care a lot, I think, if they all of a sudden didn't follow this new RFC anymore, but it would be nice, I think. And similarly to Michael's point on understanding what the stacks are doing before we make a recommendation, this is step 1 to that. But yeah, this seems like a no-brainer to do, and it shouldn't take very long, quote unquote.
Okay, so I think the question was adopting this as a working group document. So my view is we should first get the document, get in information about implementations and this stuff. We are not asking about working group adoption right now, but we would like to have a show of hands who thinks that it's good to address this area, this problem space, or who thinks it doesn't matter. So can we have a show of hands on Fernando is coming. Wait a minute.
Yeah, the connection went down. I just one response to what Lars mentioned. I agree with that. And while the document right now proposes like one workaround, the two, we could propose like 2 alternative workarounds, and that's fine. Regarding whether this should be fixed or not, I'm curious myself if you could actually move 793 Bs to standard if you actually don't fix it, because you have a requirement to actually fix known bugs.
On that one, as I said, I think there is already text on this known issue here. And the only thing that at the moment is missing, I think, in 793 bis is a change of the equation. So, I mean, I think the text already states that there is a known problem there, and there are known solutions for workarounds. And as this community could agree that that's good enough.
But can you actually move a document to full standard if the document has known problems?
Well, my understanding of the process is that 793 bis would be proposed standard, but I don't know the process out of mind. But I think it doesn't move directly to full standard if it's a bis, out of my head.
Okay.
But anyway, I mean, this document actually has a different scope than 793 bis. So because it also removes a lot of content in there, it's only the base spec. So I don't think there's a formal problem here. But of course, I mean, having a bug in a BIS document is certainly not perfect. I think we all agree on that.
Mm-hmm.
I think, given that it's clear that there, excuse me, that there are bugs in 793, excluding them from the scope of 793 BIS seems kind of artificial. It is what the words were written back when the planning was done, but this bug feels to me like it's below the horizon for a scope change, below the limit for a scope change, and important enough to do that as an exception. I really am uncomfortable with the idea of leaving 793 containing a bug that we know about, that we've known about for 2 decades.
So, okay, coming back to the show of hands, so who thinks it's a good thing that this working group deals with this issue? Not saying that this document has to be a working group document that work on this. So who thinks this should be addressed? Who is against that? Okay, thank you.
I would say for the note taker, I've seen probably of the order of 20 hands and no objection.
TCP fast open.
Hello, everyone. This is a talk on how the experience with deploying fast open on the internet has been going so far. I presented some information at the last IETF. This is more updates since then. Can we go to the next slide, please? Quick update. So we enable this by default in the fall creators update, which has been out in the market for a while now. It is the significant majority of all Windows 10 devices at this point. So the way we could enable fast open was to build a fallback algorithm. So when there are middle box problems, how do you safely recover from those? So for that, first we built a middle box that simulates all those known problems. So it also serves as kind of a regression test. If you want details on what kind of test cases we added, it's in the previous presentation. So, and then we ended up implementing a passive probing algorithm. When I say passive probing, this means that's actually using active user traffic. I shouldn't have used the word active, but it's actually using user traffic to figure out if TFO works on the network. Last time we found that around 26% devices were successfully using TFO and did not fall back. And then we also did a A/B test to see if there was any correlation, statistically significant correlation with page navigation failures, and we couldn't find any problems, which meant that the algorithm was actually working fine. We did find that there were failures that were correlated with both specific networks, geographies. Next slide, please. This is again a recap of that fallback algorithm. I wanted to quickly go over this. So this is limited passive probing. So the goal here is to not impact user experience. So when we do probing, we want to make sure that we don't sacrifice too many connections. So this is the way this works is that because establishing that TFO does work on the network requires multiple connections to the same server, which means you need multiple probe connections. But we only allow one probe connection to go through at a given time on a particular network. Think of it like a semaphore. So if you're browsing to, let's say, xyz.com, then you need to go to that site again, but it may not necessarily trigger the probe. If the previous connection was still active, the next probe will not go out. So this is sequenced in time. The other important thing is that we wait for the connection to be closed, reach the closed state before we can figure out whether the probe was successful. And then it has to match all these other conditions that, no reset was received in response to SYN, no SYN timeout, the connection didn't fully time out, data was exchanged in both directions, the connection wasn't canceled by the application, and no sudden RTT increase during any time in the connection lifetime. If all of these conditions match, then we mark the connection as probe as successful, and 2 of these probes have to succeed to the same server for us to say, hey, TFO succeeded on the network. If we hit a fallback on any of these probes, we persist that information and never attempt it again. If we hit success, then we continue using TFO for that boot session. So this was the algorithm as implemented in the fall creators update. There are some shortcomings here. The goal here was to be very conservative. We wanted to avoid any problems with the user experience, so the algorithm was actually very conservative. One of the problems is that the SYN timeout heuristic is actually a large fraction of the fallback use cases we see. In terms of if you look at the pie charts, the SYN timeout is a pretty large chunk of it, and that could be because there is just connectivity issues. And we also don't persist success, which also is very conservative, because if it succeeded on a network, it's highly likely that it will succeed again. We also assume that the problems are closer to the client and not the server. And then there are possibly long delays before we can figure out if TFO actually works. Like if you have a long-running HTTP2 connection, then for it to reach the closed state, it might take a very long time, and then you would delay enabling fast open for that duration because of the semaphore that I described earlier. The other case is like, the connection could take a very long time out if the RTT was very high. There is also the problem of the worst case middle box. Like the middle box just sees the TFO cookie request and then just blocks all traffic from that IP address. That's like the absolute worst case for TFO. And this algorithm doesn't really help. The user experience is still bad if that happens. Next slide, please. So in the next version, we are actually making the algorithm more aggressive. Firstly, we will persist now both success and fallback. So if we do see probes succeed on a particular network, that is kind of remembered forever until we decide to update the operating system again, essentially. We also will start off every device to probe again, because this is a different algorithm. So we are starting with a clean slate. So when this update goes out to the devices, they will all start probing again. Because the SYN timeout was so aggressive, we are actually now only turning off TFO if the SYN with the TFO option failed and the subsequent SYN succeeded. This kind of tells you that it was not because of network connectivity, it was because of the option. And the probing is, because of this change now, the probing doesn't have to be restricted to internet connected networks. You could exercise TFO in a private network if you wanted to. One more case that was found is that in some places, TCP options are just reflected back to the client. So if you send a cookie request, the server sends you back the cookie request option. I mean, that's just weird deployment. So we just, again, use this as a condition to turn the feature off. Next slide, please. Some more data. So this is kind of the overall population right now of retail devices out there. This is from the fall creators update, because the spring creators update is not yet deployed. 45% of devices complete TFO probing, which means they go to a TFO compatible server multiple times in that boot session.
A clarification question on the previous slide, very quickly. You said when the subsequent SYN succeeds, you only fall back if SYN fails and subsequent one succeeds. How do you define subsequent? In addition to the fact that it's happening after.
This is the SYN
time-bound.
It's a timeout and a retransmission. Yeah. So that SYN has to succeed.
It's a retransmitted SYN.
Yeah. Without the option.
Okay.
Yeah.
Very cool. Thank you.
So of those devices, then we find that overall about 46% succeed and 54% fall back. So if you look at like your overall population, it's about like 21% because the number of devices have grown. The other shortcoming I did not explain was that because we're not persisting success, it is possible that if there are connectivity failures later, the overall device population might taper over time because we're not persisting success. So if you do hit a sync timeout subsequently, a device that previously succeeded could eventually fall back. We do expect that these numbers will improve in the next update because the aggressive sync timeout logic is going away. We do find that there are some really poor success rates in some geographies. China, for example, only 3% devices that completed probing succeed with TFO, and in India it's about 18%. Those are not great numbers. And then we repeated an A/B experiment on the retail population, which is we have a much larger device population right now, and again, no significant correlation with the page navigations, which tells us that the algorithm is working as intended. Next slide, please. Looking ahead, this algorithm is really complex. So what we are looking to do is whether we can simplify this. It seems to us that one of the better ways of doing this would be to actually use active probing, which means that we don't end up using any of the user traffic to figure out if TFO works. This solves those three problems which we haven't addressed yet, which is like it could be long delays before you figure out if TFO works. User experience could still suffer if something bad happens, and then this simplifies the whole algorithm. And then the other remaining problem is if the problem is closer to the server side, and there you could do some form of happy eyeballs. This is all like looking ahead. We have not yet actually done any sort of implementation for solving these problems. One of the important things I wanted to ask is that other browsers should now consider enabling TFO on Windows because the operating system has fallback algorithm. The browsers do not need any kind of complex logic to detect if this feature works. The safety is provided in the TCP stack itself. So it should be pretty safe for browsers to turn this on and rely on the built-in fallback algorithm in the operating system. The questions I wanted to end with is 7413 seems like an important RFC to me, given that, yes, I realize that Quick is, gaining more traction, but then there are networks where it will not work and you would want to achieve zero RTT with TCP. So it seems to me like something I would recommend that this group consider whether to make it standards track. And then if we do go along that path, it might be useful to document possible fallback algorithms for dealing with middle box problems.
Jana Iyengar, thanks for the presentation. The data is great. Just a quick question on the data in the previous slide. If you can go back to that. So I know that there's one particular error that the Apple folks encountered, and I don't know if you've thought about how you might be able to provision for that. And this was when a TFO SYN was sent, the entire IP got black holed.
Yeah.
Have you thought about that?
Yeah, so I actually covered that as a shortcoming with this fallback algorithm. We cannot recover from that case. So regardless of whether you do active probing or this passive probing algorithm, you can never recover from such a case. And yeah, we are actually not seeing any kind of problems in the deployment so far, which means, such a bad case is actually not happening out there.
Right. It might be good to see if it's an A/B experiment, if the total number of connections that are failing is in fact different, like the total population of successful connections. With fallback, without fallback, everything.
Yeah, I mean, we correlated this with navigation failures in the browser, and there is no statistically significant correlation. So which means, yeah, it's not like turning on TFO is causing pages to start failing to load.
That's good to know. Although unfortunately the Apple experience still seems to suggest that even if it happens in a tiny fraction of cases, it's fatal effectively.
It is a
hopefully
error,
it's tiny enough that we can chalk it off. On the next slide, so I'll just finish this one thought before I give it back to Mirya. I believe that this is still, I believe it should still be experimental track. I absolutely believe, yes, fallback algorithms are critical to the success of anybody implementing this. So I absolutely think that fallback algorithms should be documented. And I believe that the experiment that people conduct should include fallback as well as the rest of 74.13. And we should come back to the question of whether to run it to standards track after we've had more data on both the fallback and on this from a couple of vendors. But yeah, I'd be very supportive of having the fallback algorithms in there.
Mia Kulevind, are any of your data also for connection about mobile paths?
Yeah, this is a mix. Again, I can't tell you the distribution. Like the mobile footprint of Windows is not that high compared to other operating systems. So yeah, I mean, I don't have the exact breakdown, but yes, this covers all possible devices, including Xbox consoles and.
Would probably interesting to see if there's different between mobile networks and break it down by network.
Yeah, it would be good to do that breakdown, but I think like another vendor which has a bigger mobile presence will need to do similar data collection to be able to give you a better answer for that.
So in this case, I agree with Jana that we would need more data, especially for mobile networks to move to standards track. Documenting fallbacks also a +1. I guess TFO is special, but some of the fallbacks might also apply to like every other TCP option we have probably.
Yeah, for example, ECN. So yeah.
Christoph, Apple. I had a question. What do you have like any plan for handling the unknowns? Because the way TFO can fail or mailboxes can mess up TFO is basically the number of ways that they can do it is basically infinite. One example is we found one mailbox. You send us in with data, it gets acknowledged. You can send a lot of data. You can receive gigabytes of data until you stop sending. The traffic stops for 10 seconds. After that, the connection breaks. And it was due to TFO. Like, which is why we on our side, we are still very conservative and don't dare yet to enable it globally. So how have you experienced anything like that?
So if you look at the conditions for this probe to succeed, they are very exhaustive, right? So connection should not time out. That is one of the conditions, right? So.
But do you have a 10-second idle period in the connection?
The probe connection may not, you're right. So yes, if the probe connection does not experience this, then yeah, there is no guarantees that you'll be able to recover from such a failure.
Well,
like this is again like we cannot cover like infinite cases.
Absolutely. What I'm basically saying is that there are things that we can't foresee and they still happen.
So this is Michael speaking from the floor. This is just to share my personal opinion on that, on the last question that I've said before privately. I think we are already relatively close to the data that we would need for proposed standard here. Because the one thing is we see here now pretty impressive data already. I mean, for sure we can ask for more, and that would be good, but already we have experience with it. So that's one of the prerequisites that we typically have in TCPM for moving to standards track is, from my point of view, already closely fulfilled. The second thing is we see other people using TFO now. And this is typically a sign that there is some value in doing this. And this would be, to me, another reason that this is actually clearly a candidate for PS. And PS means proposed standard. It doesn't mean internet standard.
I would agree. I think this is critical work because TCP is here to stay, whether, even if Quick takes off, I mean, you will fall back to TCP.
Matt Mathis, I wanted to suggest that at this stage, that a single data point or a very small number of data points that are really bizarre is probably not too worrying because they're probably from handcrafted boxes, for instance, specialized security appliances that are hand curated in front of no such agency. And they can have outlier bugs or outlier behaviors that we don't expect because they're defending against attacks that we don't know about. And I would bet devices that, for instance, exhibited this black hole behavior no longer do that. And so I would argue that once we get to a critical mass, all of the devices that do really strange things will disappear. because of low population.
Yes, I agree. I mean, when we did Windows scaling, there were stories of like routers rebooting and whatnot. So unless you deploy this, you're never going to move the ecosystem forward.
I also had a conversation with somebody who said, yes, please deploy because I'm trying to get my management to replace these damn things.
Jana Iyengar, I think I'm partly echoing what Matt just said, which is I don't think it's sensible to even look for 100% coverage. It's completely reasonable to have some failures, and I think that's natural, normal, and it ought to be expected. But I still think it should be, I mean, it'll be an experiment, and I think the fallback is absurdly critical. But I guess I just wanted to echo what Matt said.
Hello, this is Yoshi from Mike. About the making RFC 7413 proposed standard, I have little concern about it because we cannot use TF for any kind of TCP connection. If we can be used with TLS, then it's fine, but it's sometimes not the case. Then we have a problem for idempotency. But draft 7413 already mentioned such kind of thing. But if we make it proposed standard, we have a very solid, guideline or applicability. Without such things, it's too risky to make it proposed standard. That's my opinion, personal opinion.
Yeah, absolutely. I mean, we need to document the dangers of zero RTT. This applies to more than TFO. And then, yes, today, like Windows implementation is always doing this only on TLS connections.
Yu Changchen here. I'm not sure I agree your point about TFO being a standard, because when TFO is proposed as experimental, people already make it very clear that I have to document that the TFO requirement, particularly Bob here, that TFO is only good for item-potent applications. And that's already clearly documented. So if you want further wording, we can improve that. But I don't think this should be a barrier to the standard track.
And this is Bob. This is why I was coming up to support you, Chung, because as I don't think you should not say something can be a proposed standard just because it's got limited applicability. Otherwise, TCP wouldn't be a proposed standard because you can't use it for unreliable connections. It's sort of.
By definition, all of the work we do is limited applicability. Jana Iyengar, I had a question. Actually, I did want to also ask something else, and I forgot earlier about the data. It's very interesting that that you have such a ridiculous skew in geography. You said only 3% of connections were successful in China and 18% in India. Do you have any more insights into this? Because that seems like that seems surprising to me. 18% is a ridiculously low number, but it's half of what you were seeing otherwise on average.
All I can say is that it's not like one ISP. We see this across networks in those geographies. So it's probably some middle box. It could be the firewall. I don't know. We don't have those details at this point.
So do you have data on the type of failure that was encountered? Like, was it which of the failures that you listed out there was encountered?
Yeah, I don't have that data right now, but it would be. I think I'll try to dig that up for you offline.
I'm curious
or in the next IETF, because right now the one of the problems is that SYN timeout heuristic, which is because of just bad networks, you could hit that all the time. And that could be one reason why the success rate is so bad. And now that it's going away, in the next update, we might get different numbers. And yeah, I'll get back to you.
I had a similar thought about the subsequent, not subsequent, but connection timeout after handshake success, which could also be something to bear in mind. It might be, I don't know how to think about it, but at least in the data, it might be worthwhile normalizing that against what the normal connection timeout is for that regime, for that region, or for that particular grouping, whatever you have, just to understand if that's actually causal or not.
Yeah, that's a fair point. So again, like the goal here is to be not very aggressive, because we are using user traffic. Once we do active probing, we might be way more aggressive than this.
Yeah, I was thinking about it in terms of analysis rather than in terms of actual mechanism.
Sure. Yeah, that is useful data point to gather. Yes.
Thank you.
So any more comments? No. So I think it's looks like.
I know you want to do a show of hands on the PS.
Okay, so we want to do a
one small comment.
one small column.
Yeah. Hi, Subodh Anger. I was wondering whether you have any analysis of happy eyeballs as well, and that would be helpful to know how you guys do happy eyeballs to give some guidance on happy eyeballs usage.
We don't. So we have a custom implementation of happy eyeballs, not the algorithm in the RFC for IPv4 versus v6. For TFO, there is no happy eyeballs because we just use the user connection to probe. So if the connection was v6, which is preferred usually, we would do the probe on the v6 connection.
So we want to do a short show of hands. Who is in favor of evolving this into a PS direction?
So for the note taker, I would say 15.
Anyone against it? None. Okay, so for the last presentation, we had planned 10 minutes if they are available. We have 5 minutes available. Great, thank you.
Hello, everyone. My name is Ying Zheng from Huawei. I'm here to present the draft a new.
Eat the mic.
Okay. I'm here to present the draft a new congestion control in bandwidth guarantee network. Next slide, please. Okay, so, my co-author then presented a draft called in-band signaling for transport QoS at last IETF. So one suggestion we received from last IETF was to write a separate congestion control draft. So here we are. Here, these are the prerequisites to use this new congestion control algorithm. It's not meant to replace existing TCP congestion control. So it's only to be used for applications which has a really high bandwidth, low latency requirement that current TCP cannot satisfy. And then together with the in-band signaling, then you can use this new algorithm. So two important prerequisites. First, you have to guarantee the bandwidth before the data transmission. You can either use out-of-band or in-band signaling. And then the second, OAM data is used constantly to monitor network status. More important, it used to monitor the queue depth. Once it reaches the pre-config threshold, it will send an alarm to indicate that the network might be congested. Next. So this slide shows the congestion window comparison between the proposed algorithm and the TCP Reno. So important thing to notice is since we have the bandwidth guarantee, so we don't have slow start. In case of TCP start or fast recovery, the transmission, the congestion window can jump to CIR rate right away. And then the OAM alarm together with the duplicate ACK is used together to indicate a congestion. In that case, when that happens, the congestion window size only drops to the CIR. And in case only duplicate X are received, we don't reduce the congestion window size. So this is important. So we use OAM to detect whether it's really the duplicate package output because of real congestion or because of a random failure. Okay, so this is summary of the important changes. So it's used for bandwidth guarantee networks. We don't have slow start. We jump to CIR directly. And in case, so the congestion window size stays between CIR and PIR during congestion avoidance. And important OM is used to indicate whether network is congested or not. So the next steps, we want to collect more comments, and we want to refine our POC to collect more data, especially compare with other algorithms, also to make our the in-band signaling part work better with this algorithm together.
Thank you. This was really on time. Our schedule is now over, so that's why I would suggest get the discussion on the mailing list. It already started there. And then this concludes this meeting. Thank you for attending. See you in Montreal. And if you haven't signed the blue sheets, do it now. And bring them back.
Excuse me. I've been doing for a couple of years now to see how the server side is. I was wondering if you're interested.
Yeah.